Alright, welcome to the pre-calculus video on polynomial, rational, and radical expressions. In this video I'm going to work through examples 1, 2, and 3 in the notes packet, which focuses primarily on radical expressions. So let's get to it. Alright, starting with polynomial, rational, and radical expressions, the first thing we're going to try to figure out is how to simplify real and complex radical expressions. And more specifically, we're going to look at the real radical expressions, and then from there we'll talk a little bit about rationalizing the denominator, and then in the next video we will talk about the other two I can statements. Before we get started, it's helpful to remember some key numbers, like there's 2, and then 2 squared is 4, 2 to the third is 8, 2 to the fourth is 16, 2 to the fifth is 32, 2 to the sixth is 64. These numbers kind of pop up pretty regularly in common problems that we will be doing in this section. We also have powers of 3, so we'd have like 3, and then 3 squared is 9, 3 to the third is 27, and we have 81, 243. Usually it doesn't go much higher than that. Let's take a look also at our 4s. We have 4 squared is 16, 4 to the third is 64, 4 to the fourth is 216, and we're starting to get into some of the numbers that are a little beyond typical problems. And then finally, also there's 5, 25, 125, and 625. The reason I share these numbers is because they tend to pop up a lot, and we really should have these powers memorized because it makes solving these problems much easier. So if you write these down, it would be to your benefit, and then work at memorizing them because it'll help you move along faster. Let's jump into example 1, and we'll take a look at each one of these and start with 1a. Alright, example 1a. So what we've got here is 32, and we're taking the fifth root of it, and there are two different approaches to this. The first approach would be to very quickly realize that 32 is just 2 to the fifth, and then we can take what we learned in the previous skill and express the radical as 2 to the fifth over 5. And remember, the numerator comes from the inside and the denominator comes from the index. And 5 over 5 reduces to 1, so we have 2 to the first, and 2 to the first is just 2. Alternatively, some people might approach this with the factoring tree and see that 32 is 2 times 16, which is 2 times 8, which is 2 times 4, which is 2 times 2, and the factoring tree gives us 5 sets of 2's, so we're able to just pull out the 2. I think the factoring tree is great for some problems, like square root problems, but as soon as you start to get into third, fourth, fifth roots, that process is a little bit more difficult to follow. So I'm going to try to stick with this as the method which we use most often. Moving on to part B. Looks like we might have a complex number here. So let's scroll over here. First thing I'm going to do is split this into the fourth root of -1 times the fourth root of 625. And you're able to do that. You're allowed to pull that -1 out and then deal with each one of them separately. And let's start with the easy part, reducing the fourth root of 625. This is the fourth root of, as we saw above, 625 is 5 to the fourth, which can be expressed as 5 to the inside over the index, which is quite simply 5 to the first, or 5. So all along we also had the left-hand side, which I ignored, but now we're going to tackle. You might recall that the square root of -1 is equal to I. But we don't have the square root, we have the fourth root. So I'm going to express this slightly differently. Let's think of this as -1 to the 1/4, which we could think of, if we wanted to, as -1 to the 1/2 raised to the 1/2. Remember, we can multiply our exponents. 1/2 times 1/2 is 1/4. This allows me to think of this piece, the inner piece, as the square root of -1, which is I raised to the 1/2. And now I can see that as the square root of I. So there we go, the square root of I times 5. So our final answer is 5 square root of I. It should be noted that the I term only really comes in on the cases where we're dealing with even roots. It has nothing to do with the negative here and everything to do with the even root, because as we'll see on part C, we have a negative, but the root is odd, and we will not have a I in our final answer. So let's take this the same way we did. The third root of -1 times the third root of 27. And the third root of -1 is actually -1, because -1 times -1 times -1 is -1. And then this is, we could think of this as the third root of 3 to the third, or very simply, -1 times 3. So we get an answer of -3. I didn't show the fraction, but we could if we wanted to. 3 over 3, and that's a lot of 3's, so it's starting to get confusing. Let's take a look at the next one. Okay. Example 1D. Looks like we have several radical expressions here, and what I'm going to do is split up this 56. I see that 56 is root 7 is the first one, and then the 56 can be split into 7 times 8. So root 56 would be root 7 times root 8. And all of that is over root 2. I can collect my root 7 times root 7. That would just be 7. And then I've got the root 8 over root 2. And there's a couple different approaches we could take from here. One thing we could do is we could simplify the root 8. So the root 8 becomes, work off to the side, 7 times 2 root 2. And the root 2 in the denominator. So if you don't understand why, you could think of this as 8 is 2 times 2 times 2. And we are able to take a pair out to the outside. And that's where this 2 came from. We're left with 1 on the inside, and that's there. And in the end, we're able to cancel the root 2 on top and bottom, and we get a final answer of 14. Now, that may not have been the fastest approach. That's one approach. I'm going to kind of slide off to the side and show you that there are other approaches, and you're welcome to take your own path. The trick is you do not want any radicals in the denominator. So one other approach we could do is we could have actually combined them all to be 7 times 56 all over 2, and that's all part of the radical expression. And then we type that into a calculator, or we do the calculations ourselves. 7 times 56 divided by 2 is 196. And the square root of 196 should be 14, and it is in fact 14. So this path over here on the right, definitely a little bit faster, maybe easier to understand, but I showed this path because there's some tricks that we're going to probably need later on in the future. So one trick that seems to pop up is this root 8 is 2 root 2. And that's pretty regularly occurring. So let's take a look at 1E. All right, 1E looks a lot like a problem from the last set. We could express this as a radical expression. 16 to the 3/4 is the same thing as the 4th root of 16 to the 3rd, or we could express it as the 4th root of 16 all raised to the 3rd. either one of those values works. It just so happens that the second one probably is easier to evaluate because we know the fourth root of 16 is 2, and so what we have is 2 to the third, so this piece is 2. And 2 to the third is 8, so there's our answer. Example 1F looks like maybe we're going to try this backwards. What we have is 125 to the negative 1/3. So first off, I see a negative exponent, so I'm going to rewrite this with a positive exponent because that might make it easier to deal with. And then 125 to the 1/3 I'm going to express as a radical expression, the third root of 125. And we know 125 is 5 to the third, so what we have is 1/5 as an answer. So remember, this 125 or the denominator can be expressed as 5 to the 3/3. So there's 1F. All right, moving on to 1G. Okay, the first thing I notice is that these are both fifth roots. So let's see what happens if we express it as the fifth root of negative 3/96. And then we reduce our 3/96 to become the fifth root of, looks like negative 1/32. And I see that 32 and that rings a bell with something I remember. That's the same thing as 2 to the fifth. So what I have is the fifth root of negative 1 over the fifth root of 2 to the fifth. And that is where we can finally get to a simplification. Odd roots of negative 1 are equal to negative 1. And then the denominator reduces to 2. Okay, finally, example 1H. Okay, I see the negative exponent, and that makes me want to flip the fraction so that it becomes a positive exponent. So I'm going to go ahead and write this as 64/25 to the 3/2. That's removing the negative exponent. The next thing I'm going to do is take this 3/2 and perhaps write it as a radical expression. So this could be written as the square root of 64/25. There's the denominator of 2 raised to the third power. These are easy values to calculate. The square root of 64 is 8, and the square root of 25 is 5, and I'm raising this all to the third power. And 8 to the third, that's 8 times 8 is 64, times 8 gives us a value of 512. And then 5 to the third is 5 times 5 is 25, times 5 is 125. There we go, 512/125. All right, let's move on to example number 2. Okay, example 2, what we're trying to do is simplify a radical expression. And I'm going to start with the root 32. I know that is the same as 2 to the 5th, or I will go ahead and write all 5 2's just to make a point. 200 is maybe a little bit harder to think of this way, but let's try it out. 200 is 2 times 100, or 2 times 10 times 10. Or you could think of it as 2 times 2 times 2 times 5 times 5. So you got the 10 is, this is a 10, and then this is a 10. So what that does is it allows us to kind of group. Since we are taking the square root, which is sets of 2, we're going to pull sets of 2 out. So we've pulled 1 out, and we've pulled another out. So what we wind up having is the first set, the second set, and then the third one isn't a set, so it has to stay inside the radical. We can do the same thing with the 200. We're able to pull out a pair of 2's, we're able to pull out a pair of 5s, and we're left with the 2 by itself under the radical. So at this point, then we can simplify each piece. 2 times 2 is 4, so 4 root 2. 2 times 5 is 10, so 10 root 2. And now we can add them. Just like 4x plus 10x is 14x, 4 root 2 plus 10 root 2 is 14 root 2. So there we get our final answer. This was just kind of a placeholder to demonstrate the property that was being used. Moving on to example 2b. Let's try the same approach. We know that 75 can be rewritten as 3 times 25 or 3 times 5 times 5. And 48 can be rewritten as 6 times 8. 6 times 8 is 48, or 6 is 2 times 3, and 8 is 2 times 2 times 2. There we have the prime factorization of that number, and then we start pulling out pairs. A pair of 5s comes to the outside. 75 is 5 root 3. For 48, we have a pair of 2s, and we've got another pair of 2s, and the 3 stands by itself, so we'll leave that inside. So what we wind up having is 5 root 3 plus 4 root 3, and 5 plus 4 is 9 root 3. Okay, part C. 96 is, we'll say, the 5th root of 6 times 16, and we know that is 6 is 3 times 2, and 16 is 2 times 2 times 2 times 2. So there's 96, and the 5th root of 3 can't be simplified at all because 3 is already prime factorized, if that's even a word. Okay, here we go, using the same technique. Because we're taking the 5th root, we need to find groups of 5. So 1, 2, 3, 4, 5. There's a group of 5. We can move to the outside, and we are left with the 3 by itself on the inside. And since we have the common 5th root of 3 on both of these, 2 blank plus 1 blank is 3 blank, or in this case our blank is the 5th root of 3. So 2 plus, there's an implied 1, is 3. There we go, part C. And moving over to part D, this looks like we might have something that looks very ugly. Let's see if we can simplify this down. So let's start by getting rid of the radical symbols. So first off, we have 64x to the 12th, y to the 8 halves, and this is all raised to 1/3. So where those came from, this 8 is the numerator, this 2 is the denominator, and then all of the inside, the numerator is 1, and then the denominator 3 came from this 3. So simplifying the inside a little bit, we get 64x to the 12, y to the 4th, and this is all raised to the 1/3. And then let's distribute the 1/3 in to each term. So we have 64 to the 1/3 times x to the 12/3 times y to the 4/3. All right, 64 to the 1/3, that's the same thing as the 3rd root of 64, and I know that that is 4, because 4 to the 3rd is 64. X to the 12/3 reduces to x to the 4th, and then y to the 4/3 we could leave as y to the 4/3 and call this our final answer. Or if you wanted to write it as a radical expression, you could write it as 4x to the fourth, and then we have a y times the third root of y. So 3 of the 4 came here, and the fourth one is right here. That's where we get the 4/3. 3 of them here, and 1 of them there. I personally think this is a cleaner presentation, because I don't like radical expressions too much. All right, let's end with example number 3. Okay, this says rationalize and simplify each of the following expressions. And rationalize basically means make it so there are no radicals in the denominator. So what we have here is a radical in the denominator, which I'm going to go ahead and write as a fractional exponent. And what we want to do is get rid of that fractional exponent in the denominator. So one approach we could take is multiplying by a clever form of 1. So if we multiply the top and the bottom by 3 to the 1/2, what happens is the denominator, those two 1/2s, they add up to 3 to the 1/2 plus 1/2. And the numerator looks like 2 times 3 to the 1/2. And 1/2 plus 1/2 is 3. Sorry, 1/2 plus 1/2 is 1. So we just have a 3 in the denominator. And then in the numerator we have 2 times the square root of 3. So our final simplified answer is 2 root 3 all over 3. So what we did is we found how much more do we need to go to get to a total value of 1. So we needed a 1/2 plus a 1/2 gives me a value of 1, and that removes the fraction on the denominator. That concept will become a little bit more clear in part B. So let's try part B. What I have is 2 over x to the 2/3. If I want to get rid of that fractional exponent in the denominator, what I'm going to do is figure out how much further do I need to go from 2/3 to get to 1. And in this case, if I have 1/3, 2/3 plus 1/3 is 1. So I'm going to multiply top and bottom by x to the 1/3, because this really is just a really fancy way of writing the number 1. So multiplying top and bottom, the numerator looks like 2x to the 1/3, and the denominator looks like x to the 2/3 plus 1/3, which becomes 2x to the 1/3 over x to the 1, which is 2 times the third root of x all over x. So now the denominator has been rationalized. We took it and rewrote it so there are no radical expressions in the denominator. Let's take a look at example 3C. So first off, this has no radical expressions in the denominator, so it seems to be fair that we'd be done, but let's see if we can reduce that root 12 at all. Root 12 is the same thing as root 2 times 3, and the denominator is 4. And we seek out any pairs. So here is a pair. We can pull it to the outside, so that what we have is 2 root 3 over 4. And then the 2/4 reduces to 1/2, and then the root 3 just stays by itself. So there's our simplified answer. Some would even avoid writing that 1 and just have root 3 over 2. Okay, let's take a look at 3D. So I'm going to take this 7th root and I'm going to write it as 1 to the 1/7 and a to the 2/7. And here we've got one of those fractional exponents in the denominator that we want to get rid of. So I'm going to multiply by a clever form of 1. I need to get 5/7 more to make that denominator add up to 1. So Now what I have in the numerator, the 7th root of 1 is 1. A to the 5/7 stays by itself. And then in the denominator, 2/7 plus 5/7 is 1. So our simplified answer comes down to a to the 5/7 all over a. And if we wanted to write that as a radical expression, whoops, undo. If we wanted to write that as a radical expression, we could. It would be the 7th, not 3rd, 7th root of a to the 5th all over a. So either one of these works, but the important thing is we've removed the radical from the denominator. Okay, moving on to example 3e. So what we have here is our denominator has both a number and a radical piece. And anytime you have something where it is part number, part radical, that usually is hinting at the concept of multiplying by what is called the conjugate. So I'm going to step off to the side here and talk a little bit about the conjugate. If you have 3 plus 7 radical 4, the conjugate would be 3 minus 7 radical 4. If you have, in our case, 2 minus root 3, the conjugate would be 2 plus root 3. So all that's really changing is the sign of the radical piece. So let's do that on example E. Let's kind of set this off to the side. Example E. To get rid of the radical, we're going to multiply by the conjugate. So our conjugate is 2 plus root 3, and we multiply the top and bottom by 2 plus root 3. Because again, this is just a clever form of the number 1. So our numerator becomes 4 times 2 plus root 3, and our denominator becomes, I'll go ahead and write it out, 2 minus root 3 times 2 plus root 3. And let's start distributing. 4 times 2 is 8. 4 times root 3 is 4 root 3. Then we deal with the denominator. 2 times 2 is 4, plus 2 root 3, minus 2 root 3, and then minus square root of 3 times the square root of 3 is just 3. If we clean up everything, we get the numerator doesn't clean up at all, and then in the denominator the 2 root 3 cancels the negative 2 root 3, and 4 minus 3 is 1. There we have it. There's our answer. Dividing by 1 does nothing, so we could just write the answer as 8 plus 4 root 3. There's the simplified version. We're going to use the conjugate again in example F. So while we do not have a radical piece in the denominator, we're being asked to simplify this. Let's see what happens if we multiply by the conjugate. All right, we get radical expression, and this time it's plus 2. Radical expression, plus 2. Okay, simplifying it out. Root 4 plus h times root 4 plus h is just 4 plus h. Then we get plus 2 root minus 2 root, so that self-cancels, and then negative 2 times that is negative 4. Our denominator, I'm going to go ahead and not simplify it for now just to see what happens, and we get 4 plus h plus 2. Okay, cleaning up the numerator, we see the 4 and the negative 4 cancel each other, and we're left with h in the numerator and h in the denominator. Okay, the h's cancel, and we find that our new form is 1 over the square root of 4 plus h plus 2. Now naturally you're saying to me, well, now we have a radical in the denominator, and that's a bad thing, and I agree that it's a bad thing, but this simplification process that I took you through, we will actually use later on, and I just wanted to explore the use of conjugates elsewhere. But these two expressions, they are the same thing. I think this looks like a more simplified form, but later on, and particularly in calculus, we would want to actually have this lower form. So that's why we did that exercise, is to kind of show that we can rearrange things, and sometimes our rearranging doesn't make it look any easier. But there is actual value to what we've done. It just comes at a later time. So finally, let's do example G. And we've got another case where we have radicals in the denominator. So let's multiply the top and bottom by the conjugate of the denominator. So the conjugate of the denominator would be root x plus root y over root x plus root y. So that's just a clever form of 1. And if we take the denominator and we FOIL it, root x times root x is x. And then we have root xy minus root xy minus y. So the denominator factors or distributes out to have no radical pieces. And now we have 2 times x minus y times root x plus root y. And the benefit is we see the piece that cancels out of top and bottom, and our simplified final answer is 2 times root x plus root y. There we go. All right, that was a lot to review. Some of it was new. I hope it didn't cause too much of a headache. And don't worry, we will get time to practice in class.